right, welcome back. We're going to start off with a warm-up, so feel free, engage those around you, dust off those cobwebs from Monday, and I would like for you to model the runtime of this code in terms of n, where n is how many things are in the list that is passed in as a parameter. Go ahead, take a couple minutes. Remember what we talked about at the very end of lecture on Monday, and the poll everywhere is asking for the response to this. So it's 2:31. We'll come back together at, say, like 2:33. Go ahead. Talk to those around you. Oh. Oh yeah, it's probably a rough angle, actually. Oh, there it is. Yeah. Sure.
For the project 1 assignment, there's a reference to the C++ deck. Did you need to put that instead of the Java reference to the deck?
Is it in the, like on the web page in the instructions?
Yeah, C++.com/deck instead of docs.work.
Oh, interesting. Okay, no, thank you for, I doubt that that's what we intended. I am like literally how. Yeah, no kidding. Yeah, thank you. I appreciate that. I will definitely have somebody double check. Good. Yes, you want to look at the Java docs for things. Perfect. All right, slowly wrap up your wonderful conversations. Maybe lock in your guess on the poll everywhere. Cool. All right. Okay, let's see. Any brave groups want to give us one possible code model they came up with for this? I promise I will not put your names next to anything. Any brave? Let's see. Yes, please. N squared. Okay, so we've got one possible. And I'm going to write it like this, f of n equals n squared. Anybody have anything else? Anything different? Yeah. N squared plus n. Cool. I like it. Anybody get anything else? Yeah. Okay. Cool. Thank you. Thank you, everybody, for giving us what you talked about. Let's sort of talk about it in piecemeal then. So what this question is asking for is that mathematical function. So what we're looking for the mathematical function, that's something we call a code model. Code model. And it's the first step in our eventual journey to get to what's called asymptotic analysis, which I'm going to give you all the formal definitions for this thing called asymptotic analysis by the end of lecture today. And so when I say a code model, what I mean is I mean a function like f of n, where n represents how many pieces of information are stored in the data structure that we are executing this code against. So in this context, like I mentioned here, that is how many things are stored in list. So n really equals like list dot size. That'll tell us how, like, the value of n in this situation. And f of n should tell me how many instructions, if you want to think of it in that term, how many sort of like, really it's technically like clock cycles of code, really, is this going to take in order to accomplish its task. So we talked a little bit about what counts and what doesn't count on Monday, and I will tell you that this particular step, you can get very, very specific, and I'm going to do this really annoying teacher thing. We're going to be like, actually, the specifics don't really matter because we're just trying to get to big O, but we kind of got to take a detour through this little town on the way. And so in that context, both of these answers over here, right? These are what I would call a code model. These are a proper function, but your brains are probably already alighting on the fact that you're like, ooh, both of them have this n squared term. And so maybe this is just n squared. Like your brain already wants to jump to what the big O is. But this is the intermediary step, just for context. So when I'm trying to figure out this specific model, I'm really going to look at my code, not only line by line, but I need to look even within each line and ask myself, what's really happening in each one of those moments? So we're going to start at the top. We're going to notice that list is an array list, implemented with an array list. And then we notice we've got an outer loop, an inner loop, and then we've got like one sort of line of instruction inside the inner loop. When I'm doing this type of code modeling, I like to start, if I'm trying to figure out the iterations of a loop, I like to start first by figuring out how many things are happening at the innermost moment of the loop, and then I'm going to figure out how many times the loop iterates, and then maybe if there's an outer loop, how many times that iterates. So I sort of work from the inside out. So if I'm working from the inside out, I'm going to start with this line here. And I noticed there's actually kind of almost two things happening here. There's this bit that's the act of going into the array list and retrieving whatever element is currently stored at index 0. Now, we know this is implemented as an array list. What is the runtime of accessing an element at a given index in an array list? Constant. I love it. Yes, constant. Because we have those indices, right? Like I can just jump right in, get something out of the array and pull it out. So because it's constant, there's no term of n, and that's the most important thing we need to know. And in this context, I'm going to kind of maybe like, I count that as like, maybe that's like a +1 little instruction. And I really count anytime you access an index of an array as a +1, or anytime you access what's stored in a variable, a +1. Really, anytime you go into a specific place in memory and you pull something out, you look at a point in memory, you put something in that point in memory, you pull something out in that point in memory. Those are each kind of one count, if you will. Then, once I have pulled that thing out, then I got to print it out. So maybe that's like another +1. That's like another sort of instruction I need to do. Technically, all within the same line. Are we okay with how I got those sort of two operations? Are there any questions about that piece? This is also not necessarily the spiciest example of this, but an example of how you do need to look at everything that's happening in each line. And when I'm asking you to do these types of things, I am going to ask you to understand the runtime of a given data structure. So in order to do this, you would theoretically have had to know how an array list behaves when accessing an element in it. If, for example, instead of list.getAt0, what if this line of code was system.out.println list.get at list.size -1? Would that change the runtime at all? If I got the very last thing in the list instead of the very first thing in the list? No, I agree. Both of these are going to be constant time lookup. What if I made one more change? What if instead of an array list, it was a linked list? And you had to get the last thing in the list. What would the runtime of grabbing the last thing in a linked list be? Linear. I love it. So you can see if I made both of those changes, then what's actually happening inside the loop would be something in terms of n, right? That would be an n operation. So just wanted to give you an example of how you need to look inside of things, understand how each data structure is functioning. But we're going to go back to our original example that's a little bit kinder than that, and not my chicken scratch. So I've got two things inside of my loop. Now I want to know, okay, well, how many times is this loop going to run? Meaning it's 2 times how many times this loop's going to run. How many times does this loop run in terms of n? Yes, all of those wonderfully cautious n. Yes, it runs n times. And this is a great pattern for you to, you'll see it a ton. This sort of like start at 0, go to list.size. That in this context, right? That's n. So this loop will run n times. So now what we've got is we've got 2 times n, because that's how many times that loop is going to iterate. Now we continue to peel the onion, if you will. We go to the out loop. Oh yeah, question.
Isn't it 5n because you are making the assignment and comparison in the for loop?
Ah, thank you. What an excellent question. The question is, doesn't this count as 1? Doesn't this count as 1? Doesn't this count as 1? Shouldn't this then be 5? That's your question, right? Yeah. Okay. Here is the annoying thing about this. You are absolutely technically correct. And in this class, that will always be the best type of correct. And if I ever dock you points and you can convince me you're technically correct, I will always give you those points back. Okay? Just, I will say that aloud. Now, here's this like weird convention thing. When we're doing code modeling by convention, we ignore those extra little instructions that come from the for loop counter. So we just don't happen to count them. So we just count the for loop as however many iterations. I'll tell you why we can do that in a few bits later, but just for convention for right now, we sort of ignore any extra instructions that just come from a loop header. Does that make sense? We didn't do that with the while loop, Casey. Why is that the convention? Gosh darn it, I don't really know. I think because computer scientists just sort of wave things away, and then everybody waves things away, and now we're here. So we have some number of constant, though, happening inside of the loop, meaning something that is not dependent on a value of n. Maybe it's 2, maybe it's 5, maybe you counted 1. Honestly, all of those things would still eventually get to the right answer. But we know that the loop runs in terms of n. And that factor of n, that's the really important thing. We can't ever be off by a factor of n. We can be off by some constants because they actually don't really matter, but we can't be off by factors of n. So if my inner loop runs n times, how many times does my outer loop run? This is not a trick question. Thank you. N times. Yes. Again, I'm not trying to trick you. So we notice it has the same loop bounds. So we've got an outer loop that runs n times. And because these things are all nested inside of each other, what we really have is we have like 2 times n times n. So what does that give us? Anyone? Did I do this right? Yeah. So this is probably the code function that I would write here. However, like I said, these constants don't technically matter. We really are just trying to get to that function so that we can identify what complexity class this is in. So then my question to all of you is, what complexity class is this code running in? Quadratic. Absolutely. And so that's the answer to our warm-up question. Yes?
So I know that so this is a quadratic function, and I assume there are cubic functions as well, and we want to avoid those still because that's a factor of n that we are going to apply?
Yes. So like I said, we can be off by constants, but we can't be off by factor of n. And so in this case, for example, something that runs in linear time, very different than something that runs in quadratic time, super different from something that runs in ternary time. But you do need to keep these values, those matter. So n squared is very different from n cubed. So those sort of exponents of n, the factors of n, we need to be very cautious with those, because as you can imagine, if I had 100,000 things in a list, running that on n squared number of instructions versus n cubed number of instructions actually is going to have a monumental difference in the actual time it takes to complete that. That's a huge factor of differentials in the instructions. Any other questions on this code model? Yeah.
This is more like a technicality question. But
Sure.
if we're like going with like, you know, n squared or like a quadratic or cubic or whatever,
Mm-hmm.
and you know maybe we're also adding a I don't know a factorial or an exponential one, and would it always be like the exponential or factorial will always be the big O notation, or like in like smaller cases would you consider quadratic one?
Okay, I think what you are asking, which I am now going to decide this is what you're asking because it's such a perfect segue, is what if you have different factors of n in the same function? Like, actually, this is a really good example, right? Like, what if you have an n squared term, you have an n term, what if you have an n factorial term? Which is the correct one? That's what we're going to talk about exactly today. Yay, let's talk about some definitions. Okay, so... some quick announcements. So Project 0 is due today, due by 11:59 p.m. this evening. Project 1 releases today as well. Project 1 is also going to be a 1-week programming assignment. It's a group assignment just like before, but this one's not review anymore. We are officially starting to get into some of the course's content. And it will be due a week from today. Also, FYI, I should put on here, exercise 1. That will be out on Friday, just so you are aware. And then you'll have a week to complete that. That is the individual assignments. As a reminder, you indicate your own partners on Gradescope. So like sanity check, go back and make sure that all of your partners are associated with your Gradescope turn-in. You have to actually enter their names in and all of that good stuff. So just like go check that everybody's name is associated. You also are welcome to change partners. We literally don't care. Totally up to you. You can save the same partners, all that goodness. The default is working alone, obviously. Also, I will have office hours that are drop-in. I already have some time that you can schedule with me if you want to have a scheduled one-on-one. Here's the link to my Calendly again. Right now, I have, that's not correct. I have an hour on Wednesdays, an hour on Fridays that you can schedule. I know that might not work for everybody, so I also do have, I'm going to have Zoom drop-in office hours. They will typically be Wednesdays from 6 to 8. Unfortunately, I can't do them this week, but they will start next week. But all the TAs are, of course, here to help you with your projects. Any administrative questions? Course operation questions? Okay, fine. Yeah, okay. So let's get to that wonderful question of what happens when we have other factors of n. So where we're really at in life right now is we're trying to figure out how the heck we get from code to this concept of big O. We've kind of been doing it in 143 and up until now, where we kind of, you know, we recognize some patterns. We know if we loop over everything that's linear, we get a nested loop that's kind of quadratic, but sometimes it's not going to always be so obvious. So we need these formulaic mathematical ways to go from code to big O. We have just done something called code modeling, which takes you from code to this algebraic function that probably has a bunch of different terms and some different constants and things like that. And then eventually we need to go from there to here. And so that's why I'm like, that's what our question's really about, is how do we get from this function over to the big O? The way that we do this, and I think I've been saying this word because I can't help say this word, the way that we do this is with something called asymptotic analysis. Asymptotic analysis. And so asymptotic analysis is specifically the thing we use to refer to this sort of movement from the specifics of the code function to this idea of like, what's the overall complexity class? And really, the reason there's that sort of abstraction is because what we're trying to do is when we're analyzing code, comparing code, often the little specifics, like if this is a 2n versus say like a 4n or something like that, computers are just operating so gosh darn quickly that those types of constants really don't have a huge impact. It's which magnitude of n has the big impact overall. And so instead of looking at code and sort of like one instruction by one instruction, we're zooming out now. And we're looking instead of characterizing code within a complexity class by describing how its runtime grows as the inputs to that function grow towards infinity. Meaning we're trying to get to that asymptotic, place where we sort of like level out and we have a general understanding of the overall shape and growth rate of this code. So what does this mean? We have a function, like let's say we have a function that looks like this. And I don't know what code this necessarily came from, but you could imagine maybe we've got a loop that has like 9 things inside of it. And then does, maybe like 3 other things on the outside of the loop, and then all of that's inside of an outer loop. And then after the nested loop, there's like 3 little instructions to maybe like create a variable and then return it or something like that. I know it's weird to now be looking at just a mathematical formula, but don't forget that this mathematical formula represents some code somewhere. So how do we get from this mess to that complexity class to make it easier for us to really compare and contrast this code to determine what of this runtime is really going to have a big impact? Well, we are going to isolate what we call the dominating term. So we are going to do a bit of algebra so that we can really see what the different terms of n are. So to get from here to here, I just distributed, right? Like 3n, 9n squared. So I just multiplied that through, just to remind you, algebra. Now I can see there's really 3 terms happening here. I've got some constant work, I've got some linear work, and I've got some quadratic work, all within the same code. But as I graph this runtime, and I start to think about the runtime in relation to an ever-growing amount of inputs, very quickly we will find that the shape of this graph is dominated by that n squared behavior. And we are going to look at graphs here, but you'll find, right, like if I were to graph this just in the land of pure math, this would look like a quadratic function. It's not going to look like a line. It's not going to look like a flat plane. It's going to look like that exponential growth because that n squared term dominates or ends up dictating the vast majority of the rapidity of this growth. So we find the dominating term, which for us is n squared, and we just sort of like, you know what? We know these are just going to kind of not really contribute to the overall growth of the runtime that much. And then we literally just remove any constant factors. And that is how we now have the complexity class of n squared from the original function of 9n plus 3 times n plus 3. Maybe your eyes were really quick and right away you could look at this and you could just straight away be like, oh, boop, there's that n times n. This is going to be an n squared complexity class. But I just wanted to make sure that we break it down. You want to make sure you know exactly what the different terms of n are. And then again, because we are looking at this asymptotically, meaning as the inputs tend to infinity, the difference between like 9n squared or 2n squared or 10n squared or even 1000n squared as we tend towards infinity all sort of drop away. And that's why we treat everything in this terms of a complexity class, that everything in the quadratic space kind of functionally behaves similar to one another, but very different from something in the linear class, very different from something in, say, the n factorial class. So, yes, we would say this f of n up here, this f of n here, is in the big O of n squared. So, dominating term, drop the constants. Questions on that piece? I'm going to hit you over the head with a bunch of mathematical definitions of why we can do this. Yes?
How do you identify things like log of n or like an exponential?
Ooh, okay. So log of n is its own magnitude of n. And it is something that we will require y'all to start to understand what dominates what. And so, you know, I'm now realizing that I had it on a previous deck. Ooh, all right. Oh, we asked too much of her. Well, let's see. Hang on. While I'm doing this, I wanted to pull up. Actually, okay, fine. I'm going to attempt to go to Big O cheat sheet, and we'll see if the internet is faster than. Okay. Here is the Big O complexity chart. This is actually an incredibly helpful website. You may recognize this picture. I pulled it into a slide deck before. So here you can see a little bit of the overall ranking of the different complexity classes. This like excellent, good, fair, bad, horrible. I think that's really judgy. Big O cheat sheet. Okay, sometimes you can't help it. Sometimes you're an n squared. All right, so I don't know if I'd put this horrible judgment on things, but you can kind of see how things break out. So you'll recognize that when we're thinking about complexity classes, constant is in a class of its own, different from log n, different from n, different from n log n. And they do sort of like stack in that way, where constant time is the theoretically fastest runtime, because it's always going to be in terms of the constants that drop away, then log n, then n log n. Then up here, now we're starting to see that quadratic growth or that polynomial growth, or heaven forbid, that factorial growth. So I won't expect you to do, I'm going to try my best to avoid you having to do too much algebra, but I will expect you to understand at least these sort of complexity classes in relation to one another. Like I will expect you to recognize that n log n has a slower overall runtime and a faster growth in runtime in relation to its inputs than, say, log n. Things like that. But you can check this out, bigocheatsheet.com. There's also a lot of really helpful things in here, and we are going to essentially be filling out these tables throughout the quarter. But look, it's all nice in here. This is actually somebody made a big poster. Yes, I know people that have printed out this poster and put it like behind their computer during interviews. I don't know. You should maybe think about that. I'm not advocating. But fun tips for you. So if we come back in, let's talk about this. Can we really throw away all that info? And so really, when we're talking about Big O, what we're trying to do is we're trying to really figure out like what is significant to us when we're talking about runtime, we're comparing runtime. And so asymptotic analysis, like I said, is the analysis of a functional behavior as its input approaches infinity. So the reason that we do this is because, frankly, computers these days are so gosh darn fast. For example, I'm going to guess that most of you in 142, 143, and up until in this class, for all of those homework assignments, they ran what felt like almost instantaneously. Even though one of those programming assignments was song, and one of those programming assignments was a recursive backtracking algorithm. I think you still do that, right, in 143? Those things, even on like my Surface Pro 7, run so fast, it is essentially negligible, the difference in those situations, right? And that's because all of that code was working with such an incredibly small amount of data. Anything we have asked you to do in class, anything we will continue to ask you to do in class, if it is not using a data set that we provide for you, or data set from the internet, or data set from ML, it is a impractically small data set. When we're talking about software engineering, we are often talking about data sets in terms of millions, in terms of billions. And it's at that point where we start to need to do some really clever things about how we distribute the workload across machines, how we have to get really specific about how we design things. And so I just want you to put your brain in that kind of design land. We're designing for that type of world, not the school world where everything just sort of runs instantaneously. And so that's why this input as it approaches infinity is important, because actually that input is going to grow in orders of magnitude that you probably haven't really experienced, at least in these 3 courses, and you may not even be likely to experience unless you take like an ML class here at the University of Washington. But in industry is what you experience 100% of the time, essentially. So since we're dealing with infinity, constants and lower order terms don't meaningfully add to the final result. And so really what we're trying to do with this whole big O thing is we're just trying to come up with a shared language that we as engineers can use to quickly and effectively analyze the difference in runtime across different pieces of code. We want something simple. We want something decisive. So we have this definition of big O. Up until now, we've been doing it, like I said, kind of like a gut checky kind of thing, but now we're actually going to get into the formal mathematical definition of how we determine what is or is not in a complexity class. So let's actually talk about it in terms of graphs. Imagine you have 3 possible algorithms to choose from. So you're writing some code, maybe 3 separate developers wrote 3 different pieces of code, and all of you went through and you wrote the code models for your code. So some engineer, theirs runs in 4n time. So maybe that means they have a for loop that does 4 instructions inside of it. This engineer runs in n squared time, so maybe they have a nested loop. This engineer runs in n time because, I don't know, maybe hashing is the secret to everything. That joke will land way better after we do the hashing unit, y'all. And so when we think about the runtime of these different pieces of code, we are going to think about how we graph that runtime in relation to the inputs. So here we have the number of inputs, so like 0 inputs down here, and then the time it takes for our function to execute. So this is also like f of n, right? As we've been doing it. So you can see here, we've got a couple linear relationships, right? So for f of n and g of n. So like, let's say this is like 5 inputs. For f of n, that means that there will be 5 instructions, right? For 4n, that means there will be like 20 instructions accomplished. And then if we come all the way out here and maybe this is 10 inputs, then, like that's 10 instructions. I can do orders of magnitude here, I guess, and then here, maybe this is like 40. So we're graphing the number of inputs against how long it takes our code to run. So we can see that as the code maybe lives in our ecosystem, maybe n is the number of users in our database that we have to search through to find the username and password that they plugged in. And wow, in the beginning, when we only have 10 users, who cares? N squared, n, whatever, it doesn't matter. But what if we had, I don't know, 1 billion users? You could imagine the time it takes to finish something in n squared time with 1 billion is a lot different than the time it takes to finish something in n with 1 billion. As we then zoom out and n gets larger and larger, so now n is, closer to approaching infinity, here's that h of n graphed here. But we can see that even though the f of n and g of n, they did have this factor of 4 as a difference. As we zoom out and look at larger and larger values of n, it's almost like they kind of end up collapsing on top of each other because that little 4 in relation to infinity just becomes so negligible. But we do see this distinct growth difference between the n squared and the linears. And it's almost like, oh, look, it's almost like this is one category of growth and this is one category of growth. It's like this is one class of growth, one complexity class. So we can see that those growth rates are so dominated by the term of n that the little factors of, say, like a coefficient or an extra little constant at the end, they just ultimately sort of fade away in comparison. And that's why we are trying to simplify down to these complexity classes so that we can really decide how we're going to spend our time debating things. Because you'll find that debating over whether or not you can eliminate this 4 versus, not, that's probably going to waste a lot of your developers' time, as opposed to oh, I want to know right away if my stuff runs in n squared time. It's probably worth my time to invest and figure out if I can get that down to linear. Those are where the big jumps, the big improvements are. But maybe you're that person in class that's but Casey, n squared isn't always gonna grow more quickly than linear. What about this magical moment right here? And this magical moment, I believe, is a value of 1 in this case. Like, what about this? Look at now, the n squared is down on the bottom. Maybe in some situations, n squared is a faster equation. And yes, that is something we are going to keep in mind. So when we get to our formal definition of big O, we would say that a function, f of n, and we say it in this weird way where we say it's in the set of this complexity class, because you can think of the complexity classes as like a set, right? It's like it's in the category of. So f of n, and then in case you're not familiar, this is the mathematical symbol for in the set of. So we would write something like this. F of n is in the big O of, like, let's say n squared or something like that. That's how we would write the complexity class and then our function. We would say that is true if there exists positive constants c and n naught such that for all n beyond n naught, f of n is either less than or equal to some constant factor times the complexity class. What on earth does this mean? So let's say we had f of n equals 4n. We are saying this is in the complexity class of O of n because there exists positive constants such that 4n is always less than or equal to some constant c times n, where all n's are greater than or equal to n naught. That n naught, that could be that value of 1 from that previous slide. So that n naught lets us sort of like ignore little situations like this. The n naught is sort of like, well, after this value of n, that growth rate is just always faster. So ignore any, and like maybe that n naught changes in some situations. Maybe it's like your code has this really fast runtime when you have under 10 items. But then after that, its growth rate's really consistent, things like that. So the n naught is that moment, that number of inputs after which the growth rate is always in this complexity class. And then the c, that really just means as long as they have the same order of n, but the only difference is some type of coefficient. So, in this case, we could say pick a c that's like 5n, and we would say, well, 4n is always less than or equal to 5n, so they're all in that complexity class. The other way that we say it, and I know this feels weird, is you would say something like g of n dominates fn. That is technically the mathematical term for this idea that big O is the upper bound. It is the top of the growth rate of this function. Okay, let's see. Thank you, past Casey. Much better to have actual graphs. So you can see here y n naught. Like I said, it's that moment in time after which these things are forever true. So you can see here what's happening is here's a function that grows in n time. Here's a function that grows in 10 log n time. And so apparently before the value of like 30 something, I can't remember what it is, the linear runtime actually is faster. But logarithmic time, it kind of has that like it's faster growth rate in the beginning and then it kind of levels out. And so that's why n naught is so important, so that we can say, well, we don't really care about these values, right? We only care as n goes to infinity. So we're saying like, hey, we'll pick n naught at 40 and we just care about the growth rate in this part as we head out. And so in this situation, we can see that like the n is always going to grow faster, is going to take longer to execute than the logarithmic, because we can pick this moment in time. The c is because this growth rate is technically the same. They're both logarithmic growth rate, but like I said, when we zoom out, they end up having the same sort of growth rate. So as long as the rate of growth is the same except for a coefficient, then they're in the same complexity class. Now, if you were to join the CS department and take the CS majors version of this course, which is 332, this would be the portion of the course where I'm like, get ready, we're going to write a bunch of mathematical proofs for the next week. And that's actually what the CS majors have to do. But we all got around and I was like, hey, do we actually need that? Or is that just for a bunch of theoretical computer science stuff after this? And we all decided, no, let's not make the non-majors do that at all. So you're not going to be asked to do proofs in this class. The next few slides include a bunch of mathematical proofs. If you're that type of person and you want to read through it and understand, you can see how we do that. But all this is just mathematical symbolism for showing you what I just showed you on the previous slide. That as long as there is an end not after which those growth rates have the same sort of relationship, and as long as the growths are only differing by a coefficient. Any questions? I'm going to interpret that delightful murmur as like, oh, thank goodness, no problem. Yeah, okay. Like I said, that's in here if you want to get into it. Here, I will say in previous times I taught this course, I did make everybody do proofs because this literally was me just taking the majors version class and teaching it to non-majors, and I was like, screw it, it's my class, take it out. So here's another example if you want to show it. And really, this is just going through some mathematical representations to make sure that you can find an example C and an example and not to make this true. Here is more instructions on how to write big O proofs. So where am I really heading with all this big O proof stuff? Like I said, I'm just trying to convince you that these things are true. But really, what I am actually also trying to show you is we have a mathematical reason why we can wave away some of that information. But what I'm really trying to get at here is I'm trying to find that sort of representative growth rate that upper bounds the growth rate. That's what big O is. It's the upper bound. Now, here's the thing about the big O definition. The big O definition really comes down to this single character. As long as f of n is less than or greater to, g of n, c times. So that's the definition of big O. So here, for example, is f of n, let's say that's the code function. Let's say it's n plus 3. Make it look a little different. And let's say g of n, let's say that's n squared. Do these two functions, f of n and g of n, do they satisfy this rule? Is n plus 3 always going to be less than or equal to n squared given some n naught moment and some coefficients? Yeah, I see nodding. Great. Okay, cool. I agree. So what about if g of n wasn't n squared? What if it was instead n cubed? Is this still true? Yeah, I agree. What if instead this was n factorial? Yes. So big O, by definition, is just a complexity class, a growth rate that dominates your growth rate, i.e. just something that upper bounds it. But by definition, not necessarily fits it. And you might be like, why do we do it this way? And it's because, for example, sometimes it's easier to just be like, hey, just so you know, the servers can handle up to n squared on a billion items. As long as your stuff fits under there, we're good to go. I don't care if you're using n, I don't care if you're using constant, I don't care if you're using n squared, just don't do n cubed, right? Sometimes we need to talk in that way. So big O is technically just an upper bound, but it doesn't have to be a good upper bound. I mean, it doesn't have to be an actual fit. It's an upper bound. Yes.
So is there a little O?
Ooh. Is there a little O? Man, what an amazing segue question. I shall answer that question for you, I think, in a slide. Great question. I will just land here to finish this slide real quickly with this one little last joke. We didn't used to make this joke in class, and then inevitably every quarter some student would make this joke and think that they were the first person to ever come up with this joke. And so if you are in an interview and the engineer says, what is the big O of this function? You might be like, well, I took Casey's 373 class and I actually paid attention kind of during that proof section where she told me that really big O is just this upper bound. So technically I am correct if I just say, hey, the big O is n factorial. Because like, yeah, if you have somehow managed to write code that is not dominated by n factorial, you got a lot of other problems, all right? This is not the answer they're looking for, but the engineers will not say it in the way that is technically true. So if you want to give somebody what is more like the fit of the like tightest upper bound, we're going to use what we call the simplified tight big O bound. And that is the complexity class that is as close as possible to the upper limit of the growth rate. Like I said, it happened on exams. People wrote, haha, n factorial is right for everything. And I was like, gosh darn you for being technically correct. And now I had to put the slide in here. Okay, so these are more slides about that. It's a upper bound. It's not an exact bound. Here we go. So here you can see, like, here's n squared. Here is n cubed. Here's n to the 4. Here's n to the 5. Those are all different. We can see that this is clearly dominated by all of these things. So you could technically say n to the 5 is a big O of this 10n squared. Not a simplified tight big O, but a big O. So, wow. I literally don't even know why. Okay, so here to answer our what about the little o question, which is we have to get through this before you go to section tomorrow. What if we had a piece of code whose runtime looked like this? And you might be like, Casey, what type of code would ever run like this? This code actually here, but I'll like fix these animations. What this code is this is checking if a number is a prime number. And the way that you check if a number is a prime number is you literally check if every number smaller than the square root of it fits into it. So if you're like, hey, is 3 a prime number? Does 1 fit into 3? Does 2 fit into 3? Does 3, like that kind of thing. And so it's very, very fast, as you can imagine, to determine that an even number is not a prime number. But when you are trying to find prime numbers, you have to do it by order, like process of elimination. So whenever you're looking for the prime number, that takes a lot longer. So you get this super weird growth rate where when n is an even number, it's like this really kind of nice, almost flat constant, right? Because you just check, hey, is it divisible by 2? Boom, not a prime number. Versus the larger the prime number, the longer you have to run in order to find all of the things underneath it to determine it's not a prime number. So this growth rate's real wonky. It looks all over the map. How can we use our big O notation in order to accurately express the weirdness of this kind of growth rate? Well, we can use big O and we can recognize, well, like, you know what? In this situation, n is a totally accurate big O, right? Linear is always going to dominate this. It essentially ignores this piece of it, but it gives us that like worst case scenario situation is what a lot of people are looking at. But it doesn't feel very precise, right? So big O isn't everything. Welcome to, I like little o, but technically is something we would call big omega. So big omega is the exact same thing as big O, but instead of looking for something that is the upper bound, it is looking for something that is the lower bound. Notice it's the exact same definition. It follows the exact same sort of ideas, but it's the lower bound of the growth rate instead of the upper bound. So in this particular is prime example, we would say the big O is linear and the big omega is constant. One more definition for y'all. Sometimes we might have a different big O from a different big omega. Sometimes the upper bound of the growth rate is different from the lower bound of the growth rate. sometimes we want to have a term specifically to mean that, like, what the heck is that fit thing? So we don't have that weird, like, haha, n factorial joke. So here's your final definition, big theta. Big theta, and if you look, big theta is officially that in-between moment. So big O is the upper bound, big omega is the lower bound, and big theta is the fit. I will probably go through more of these. Really? Okay. There we go. But you can see here, for example, 4n squared, that is in the big omega of constant, meaning it's lower bounded by constant, it's lower bounded by linear. It is technically lower bounded by its own complexity class, but it is not lower bounded by n cubed, versus in the big O set, it is not upper bounded by constant, it is not upper bounded by linear. It is technically upper bounded by itself, but then it is upper bounded by m cubed. That's how you determine that the theta is n squared. Okay? Go to section tomorrow. The TAs will help reinforce this. Big O, big omega, and big theta. Thanks so much, everybody.